Assalamualaikum warahmatullahi wabarakatuh. Good day, everybody. Today, we would like to present our presentation about simple linear regression. Now, the first one to present is Loisa, Hosiana, Naibaho. The second one is Syifa Nabilah, and the third one is Inayah, Ummi, Hanny, and the last one is me, Farhan Nafily. And here is the presentation.
Simple linear regression, the collection of statistical tools that are used to model and explore relationships between variables that are related in a non-deterministic manner, is called regression analysis. The concept of regression analysis deals with finding the best between y and x, quantifying the strength of the relationship, and using methods that allowed for prediction of the response values given values of the regressive x. This is the formula for simple linear regression, where beta 0 is the intercept and beta 1 is the slope. The resulting analysis of the single regressive case is called simple linear regression. This is the model for simple linear regression. The quantity y is random variable. Since e is random, the value x of the regressive variable is not random and in fact is measured with negligible error. The quantity e, often called a random error or random disturbance, has constant variance. This portion of assumption is often called the homogeneous variance assumption. The method of least square German scientist Carl Gauss proposed estimating the parameters beta 0 and beta 1 to minimize the sum of the squares of the vertical deviation, that called the method of least square. We may express an observation and a sample like this, and the formula for the sum of the square of the deviation of the observation from the true regression line is like this. And least square normal equation normally like this. For least square estimates, to estimate the intercept and the slope, we can use the formulas like this. And the fit of our estimate regression line is therefore y-axis equal to beta 0 axis plus beta 1 multiplied by x. Note that each pair of observations satisfies the relationship like this, where E is residual. Residual is describe the error in the fit of the model to the I observation Y.
Okay, next slide is properties of the least squares estimators. This is the model of the assumption that the error term, where yi equals beta 0 plus beta 1 times xi plus ei, is a random variable with mean 0 and constant variance, or tau power by 2. Suppose that we make the further assumption that ei or E1, E2, blah 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 until En are independent from run to run in the experiments. This provides a foundation for finding the means and variance for the estimators of beta 0 and beta 1. It is important to remember that our value of beta 0 and beta 1, based on the given sample of n observation, are only estimates or two parameters beta 0 and beta 1. If the experiment is repeated over and over again, each time using the same fixed value of x. The resulting estimator of beta 0 and beta 1 will most likely differ from experiment to experiment. Since the value of x remain fixed, the value of beta 0 and beta 1 depend on the variation in the value of y, or more precisely on the values of random variables. The distributional assumption implies that y, I, where I is equal 1, 2, blah 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 until n, are also independently distribute, with mean is, this is the formula of mean, and equal variance to power by 2 is that this is the formula of variance for where I equals 1 until n. And next is mean and variance of estimators. This is the formula of mean. This is the formula of mean estimators. To find the value of mean estimators, we have to know the value of beta 0. So we can find the value of mean estimators. And to find the value of variance estimators, we have to know the value of xi and x bar. And after that, we calculate based on the formula. So we can find the value of different estimators. Next is partition of total variability and estimation of tau power by 2 or variance. To draw inference beta 0 and beta 1, it becomes necessary to arrive at the estimate of the parameter tau power by 2 appearing in the two preceding variance formula for beta 0 and beta 1. The parameter tau power by 2, the model error variance, reflects random variation or experimental error variation around the regression line. This is advantageous to use the notation. This is the notation and the formula of SXX, where to find the value of SXX, we have to calculate the formula. We have to know xi and x bar. And this is the formula of SYY, where we want to get the value of SYY, we have to calculate this formula where we have to know yi and y bar. And this is the formula of SXY. To find the value of SXY, we have to know the value of XY, X bar, YI, and Y bar. And we calculate the formula so we can get the SXY. After that, we write the error sum squares as follow. This is the formula of SSE, where before we get this formula, this is the original formula of SE, and after we calculate this, so we can get the final formula like this. And this is the formula of beta 1, where the formula is beta 1 equals SXY per SXX. And this is the estimate of variance. The formula of variance, or S power by 2, is equal SSE per N minus 2. And then the estimator of tau power by 2 as a mean square error. This is the formula of the tau power by 2 as a mean square error. S power by 2 equals sigma of yi minus yi bar power by 2 per n minus 2.
Okay, today I want to explain about assessing the utility of the model and the coefficient of correlation and determination. First, the coefficient of determination. A widely used measure for a regression model is the following ratio of sum of squares, and the formula is, as you can see in the presentation. The coefficient is often used to judge the adequacy of a regression model. The statistic of r to the power of 2 should be used with caution, because it is always possible to make r to the power of 2 unity by simply adding enough terms to the model. For example, we can obtain a perfect fit to n data points with a polynomial of degree n minus 1. In general, r to the power of 2 will increase if we add a variable to the model, but this does not necessarily imply that the new model is superior to the old one, unless the error sum of squares in the new model will have a larger error mean square than the old one because of the loss of one error degree of freedom. Thus, the new model will actually be worse than the old one. The magnitude of r to the power of 2 is also impacted by the dispersion of the variable x. The larger the dispersion, the larger the value of r to the power of 2 will usually be. The next is about misconceptions about r to the power of 2. In general, r to the power of 2 does not measure the magnitude of the slope of the regression line. A large value of r to the power of 2 does not imply a steep slope. Furthermore, r to the power of 2 does not measure the appropriateness of the model, because it can be artificially inflated by adding higher-order polynomial terms in x to the model. Even if y and x are related in a nonlinear fashion, r to the power of 2 will often be large. Finally, even though r to the power of 2 is large, this does not necessarily imply that the regression model will provide accurate predictions of future observations. Next is the coefficient of correlation and determination. Coefficient of correlation assume that X is a mathematical variable measured with a negligible error and that Y is a random variable. Many applications of regression analysis involve situations in which both X and Y are random variables. In these situations, it is usually assumed that the observations xi, yi, I is 1, 2, until n are generally distributed random variables obtained from these distributions. Recall the correlation coefficient is defined as, and the formula is here, where you can see this is the covariance between y and x.
Okay, the last topic is using the model for prediction and estimation. Okay, here is the formula for confidence interval for estimation, and it is the formula for prediction interval. As you can see, there are two formula in confidence interval for estimation. The first one is used to find confidence interval on the slope b, while the second one is used for confidence interval on the intercept b. Now let's jump to the example. This is the example. This is the table for oxygen and hydrocarbon levels. And the objective is to find 95% prediction interval at x0, 1 and y0 89.23. Okay, we use the prediction interval formula in here. The y0 is 89.23. The t value we find on the table is 2.101. The variance, we use this formula. And the x-axis, we use this formula. And the x bar is the mean for the value of x. And this is the initial number. As you can see, the y0 is 89.23, the t is 2.101, the variance is 1.18, the x-axis is 0.68, and the x bar is 1.1960. After that, we do some calculation and some math, and the result is 86.83 less than equal of y0 and less than equal of 91.63. Alright, that's all about the presentation. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.